The next thing I want to talk about is electroplating. I want you to understand what electroplating is and the concepts behind it, and be able to perform calculations involving electrolysis or electroplating and the following relationships: your charge and current, how it relates to each other with time. Now, what is electroplating? Electroplating is when I take a substrate, so some kind of substance, and I plate or I reduce another metal onto it. For example, in the picture shown here, we have an object to be plated. It's some kind of usually metal surface. It doesn't have to be metal, oftentimes a metal surface. And we plate something onto here. So in this example here, we can see that silver ions are being plated onto it. We call it plating. It's just a terminology within the industry, but it's being reduced. So what we see is that silver ions are being reduced not just at the cathode, but onto the cathode. I apologize, that's supposed to say the. So when we're plating something, it's reduced at the cathode, but it also sticks there then. So it's going to stick to the cathode. And note, at the anode, I have silver being produced. So what I'm doing is I'm putting a silver electrode in that is the source of the silver ions. I have some silver ions in solution as well, and then I'm plating them at the cathode. Your cathode is what we call your substrate. It's what object is actually being plated, what I'm putting things onto. Cations are reduced at the surface, and those cations plate onto or stick to the surface of the substrate as a reduced species. As a reduced species. Now, your anode is what we call your counter electrode. The anode could be a number of things. It could be the metal that's actually being oxidized. By using the same metal, we're replenishing cations within the solution. That's what's shown here in the photo. It could also be just another type of counter electron where oxidation is occurring. So it could be some other type of metal that is being, or an alloy of metals that are being used where oxidation occurs. Because again, we cannot have reduction at the cathode without oxidation occurring elsewhere. We have to complete the circuit. So I will play this video separately and import it into here. I can't get it to play through the PDF in here, but it just shows a quick video of an electroplating system itself. So let's go ahead and play. You're also going to electroplate a piece of iron wire. If you watch closely here on the video, this is actually electroplating this piece of wire. We can see here, I apologize, the solution is actually, you can see the metal particles growing on here, and if you look over here, you can see the solution actually moving as the zinc is coming off of the zinc electrode and plating onto the iron electrode. So we see the zinc electrode over here being dissolved, and the iron electrode being plated onto. At the end, this is the final picture of the zinc being oxidized, and it's being reduced onto the iron electrode. So we're plating zinc onto iron. Again, you can see the zinc being oxidized off of the zinc metal and being plated onto the iron. So again, that video is just showing you what electroplating looks like. Let's go ahead and talk about some things we need in here. We are actually going to calculate how much current goes through, how much time goes through, how much charge goes through a system during electroplating itself. But first we need to define some things. Let's define current. Current, we use the capital letter I to define. And current is equal to lowercase q
over T. Now here, these things mean a little bit different than we've learned before. I is our current, which is measured in amps. Capital A. Q does not mean heat here. It's not thermochemistry. Q means charge, which is measured in coulombs. Capital C. And T is time, but specifically in seconds, lowercase s. 1 amp is equal to 1 coulomb per second. And then 1 mole of electrons carries 1 joule of charge. One joule is equal to 96,485 coulombs per 1 mole of electrons. This number is known as Faraday's constant. You'll see some people report it as 96,500. That's fine. I use 96,485 just as how I have it memorized. So Faraday's law tells us that the amount of metal deposited during electrolysis, again, electrolysis means non-spontaneous process. I'm applying electricity from an outside source. The amount of metal deposited during electrolysis is directly proportional to the charge on the cation, the current, and the length of time the cell runs. So what is my charge? What is my current? And what is my time? Again, 1 Faraday, capital F, is equal to 1 mole of electrons equals 96,485 coulombs. It's 1 mole of electrons passed in the system. It's implied in the definition. What that means, though, is that if a current equivalent to 3 moles of electrons is passed through a solution of gold 3 plus, then 1 mole of gold metal will be deposited. Because there's a 3 plus charge, it needs 3 moles of electrons to completely reduce it. From silver 3 plus, I keep saying silver, I really mean gold, and I apologize, and I'm trying to write silver. Gold 3 plus needs 3 moles of electrons to reduce itself all the way down to gold solid. Let's work some examples. This is the general pattern that you will be given. Current and time, if you're given current and time, find the product of current and time. That gives you charge. Use Faraday as a conversion factor. Moles of electrons, use the coefficients of the balanced equation to find the ratios. Moles of product, use the molar mass, a standard molar volume as conversion factor, grams or liters of product. So generally speaking, you can follow this pattern, but let's look at it from a couple different directions on just how you can do it. Again, it is just stoic at this point. We're just adding in 1 or 2 things that you haven't seen before, thinking about like moles of electrons passed. So, example 1. What mass of copper will be plated out from a solution of copper 2 sulfate if a current of 10 amps is applied for 10 minutes? Let's think about what I got here. Number 1, I know that my current is equal to my charge over time. I'm trying to find mass of copper, and I'm given current, and I'm given time. I also know that it's copper sulfate, which is copper 2 plus. Copper 2 plus will gain 2 electrons, forming copper solid. I know 10.0 amps is equal to Q over 10.0 seconds. So I can quickly find my charge. Q is equal to I times T, 10.0 amps. And it may be helpful at this point to rewrite amps as coulomb per second times 10.0 seconds. That is not 10.0 seconds. That is 10.0 minutes. I need to put that into seconds. I apologize. I need this into seconds. So 600 seconds. I'm going to put a decimal place right there to emphasize that I still have 3 sig figs. 600 seconds. gives me 6,000 coulombs. So I know that in 10 minutes, 6,000 coulombs of charge has passed. Now I'm going to find the grams of copper. I know my sig figs are here. Underline it. You can also put this in scientific notation if it makes you feel better. I don't care. I'm just going to underline what my sig figs are. 6,000 coulombs. I know that 1 mole of electrons is 96,485 coulombs of charge. So that cancels out my coulombs. I've got moles of electrons. I know that 1 mole of copper solid requires 2 moles of electrons to be passed, because it's a +2 charge on the copper, because it's copper 2 sulfate. Now I've got moles of copper. I know the atomic weight of copper is 63.55 grams to 1 mole. Calculate that out. 3 sig figs, 1.89 grams of copper metal will be plated out. Does that mean it will actually be plated out? I mean, in a perfect scenario, yes. We do know that things are not perfect when it comes to laboratory experiments. However, perfect scenario, we could get out just under 2 grams of copper metal under this system. Let's work another example. What current is required to plate out 10 grams of silver from a solution of silver nitrate in 1 hour? So what are we thinking about here? Well, we know that we want to know current. So we're trying to find I. We're given grams of silver and we're given time. We're given time in hours, we need to get that to seconds. I know my current is equal to my charge over my time. I'm trying to find this. And I know 1 hour, you can do the calculation, or you can just, you can do the calculation throughout if you would like, but this is equal to 3,600 seconds. So, I need to find this numerator here so that I can find my answer. I know that I've got silver. Silver, first of all, only has a +1 oxidation, +1 charge for oxidation state. It's either +1 or 0. But it is silver nitrate. That also tells me I know nitrate is -1 charge. So that also reiterates that silver is a +1 charge. If I do not remember that silver is always a +1 charge. Gains 1 electron, forming silver solid. So let's find the number of coulombs, or Q. I'm told that I'm plating out 10 grams of silver. Even if I forget the process, I know that normally if I'm starting with grams, I gotta convert to moles, and it's no different now. So I'm gonna go ahead and convert to moles. 107.87 grams of silver. That cancels out my grams of silver. I've got moles of silver. Well, I know that based on my balanced equation here, for every 1 mole of silver produced, 1 mole of electrons must be transferred. So 1 mole of electrons, 1 mole of silver. And I know Faraday's constant, 96,485 coulombs is equal to 1 mole of electrons transferred. This gives me 8,942 coulombs. Got underline my sig figs there. It does have 3 sig figs. Now I'm ready to plug it in up here and find my actual current. 8,942 coulombs. Again, just underlining where my sig figs are at, and I get 2.48 amps. Again, I can write that as 2.48 coulombs per second. So that is the same thing. Just amps just looks more proper for my current, but it is the same answer. How about this one? How long would it take to plate out 5 grams of solid nickel from a solution of nickel 2 sulfate under constant current of 5 amps? So now I'm trying to find time. I've got mass, I've got current, what can I do? Well, let's see. We know we've got nickel 2+. Nickel really likes to be 2+, but it's also nickel 2 sulfate, so we know it's a 2+. Gains 2 electrons to form nickel solid. I know that current is equal to charge over time. I'm trying to find time, so I can take charge divided by current to find time. I know that my current is 5 amps. I do not know my charge. So that must be what I'm trying to solve for now, is my charge. So number of coulombs, or Q, that's passed in the system. I've got 5 grams of nickel. Again, even if I don't know what else to do, I'm pretty sure I'm gonna convert to moles here, because that's pretty much what we always do, right? We have to compare through moles, because again, moles is telling me the exact number of nickel ions being reduced, the exact number of nickel atoms being reduced. Like, how many specific pieces do I have? Atomic weight of nickel is 58.69 grams per mole. Now that is nickel 2+, so I do need 2 moles of electrons transferred for every 1 mole of nickel reduced. And I don't put them in here, but you can absolutely say things like, 1 mole of nickel 2+ to 1 mole of nickel and import that into here if it makes more sense to your brain. I don't, because it doesn't matter, but because it'll be a 1-to-1 ratio every time. But if that makes more sense to your brain, please feel free to do that. Let's see, where are we? We've gotten rid of grams, we've gotten rid of moles. We need to get rid of moles of electrons. We know it's 96,485 coulombs for every 1 mole of electrons. And so that gives us our answer. Let's see, 16,440 coulombs have passed. We do have 3 sig figs, so I'm going to underline the 4 right there. Now I am ready to go ahead and find my time. 16,440 coulombs passed. .00 amps gives me 3,288 seconds. Now this question doesn't specify. I could leave it in that unit, but most of us aren't going to be able to quickly relate what 3,300 seconds mean in our brain. So I'm going to go ahead and convert that to minutes. 1 minute to 60 seconds. 54.8 minutes. So it's going to take just under an hour, which may sound like a long time, but in the world of electroplating, it's actually pretty quick. So about just under an hour to electroplate 5 grams of nickel. Let's see, what is the next one? How long in hours would it take to produce 25 grams of chromium from a solution of Cr3+ by a current of 2.75 amps? So I've got my current, I know my mass, I want to find time, this time specifically in hours. It's going to give it to me in seconds, I'm just going to have to convert. So let's see, let's do it all in one fell swoop. Number of hours. I want 25 grams of chromium. 1 mole of chromium weighs 52 grams. Again, I don't do it in here, but you are more than welcome to say 1 mole of Cr3+ to 1 mole of Cr. It's more correct because you're seeing everything cancel out properly that way. I do know that 3 moles of electrons are transferred for every 1 mole of chromium 3+ reduced. I've run out of room, so I'm going to write down here. But I know that it's 96,485 coulombs for every 1 mole of electrons transferred. I'm into coulombs. Now I just need to use that current, where that's 2.75 amps is the same as 2.75 coulombs per second. I can use that as conversion factor, right? I know 1 second is 2.75 amps. So, 2.75, I'm doing well, coulombs. Just reiterating that we don't always have to do it in multiple steps. We can do it all together. That's going to give me my seconds. Go ahead and convert to hours. I know that 1 hour contains 3,600 seconds. From doing way too many practice problems, I have that memorized. Let's see, and this will equal 14 hours. Which, again, sounds like a really long time. It's not quick, but it's not long in the world of electrochem. Okay. Last example. Calculate the mass of silver that... I keep saying silver. Gold. It's definitely gold. I apologize. Calculate the mass of gold that can be plated in 25 minutes using 5.5 amps for the half reaction. Gold 3 plus, gaining 3 electrons, giving me gold solid. So number of grams of gold. 25 minutes. I forgot to reiterate up here. I apologize. I had 2 sig figs here, so I have 2 sig figs here. So 25 minutes. I know that 60 seconds are in 1 minute. Time, current, okay. I know that 5.5 coulombs are transferred per second, because that's what my current's telling me, right? So let's see what we've canceled out now. We've canceled out our minutes, our seconds, we've got coulombs. I know that 1 mole of electrons is transferred for every 96,485 coulombs of charge. I know that 1 mole of gold 3 plus is produced or is reduced for every 3 moles of electrons transferred. Again, you are welcome to say, 1 mole of gold. I apologize, it's getting so messy. It's hard for me to write on the bottom of the screen. 1 mole gold to 1 mole of gold 3 plus. Again, just kind of reiterating where those values are coming from, how we're transferring. Atomic weight of gold, 197 grams to 1 mole. 5.6 grams of gold. And again, we start off with 2 sig figs here, 2 sig figs here, 2 sig figs to finish. So most students don't mind these problems. They seem pretty simple after everything you've been through in Chem 2. I hope that's the case. It's basic stoic. It's just really remembering how many moles of electrons are being transferred and then Faraday's constant.